Welcome to today's Back to the Drawing Board lecture series hosted by UCC Architecture Society. Today we have myself, Niamh and Alice McCarthy from UCC Architecture Society, and we are joined by Paul McNally from PassivHaus Architecture Company, which is based here in Cork. Paul McNally is a RIAI architect and director of PassivHaus Architecture Company, with over 20 years of experience in the field. So with passive architecture, it's basically been brought about because of issues with climate change and how the building sector is a big, I suppose, it causes a lot of issues in sustainability and how buildings are made, and with embodied energy and carbon emissions. So we look at it in a different approach, maybe how we can make buildings passive but also sustainable and comfortable to live in. So that's what Paul will be discussing today with reference to a few of his examples. And then myself and Alice will be leading a conversation with Paul afterwards. I'd also just like to mention that this is part of UCC Green Week. So that's why we have, and like sustainability architecture is a big part of that. So that's why we're bringing it as part of it. So I'll pass it over to Paul now to start the presentation.
Okay, thanks very much, Niamh and Alice, and I'm going to just share my screen now. Okay, so yeah, my name is Paul McNally, and as well as being in private practice, I am a part-time lecturer in CCAE, that's the architecture school in UCC. And I'm teaching second years, third years and fourth years environmental design and design technology. So my practice, I've been practicing for about 20 years, yeah, since about 2002 or 2004 actually. I set up my own practice. So I've got about 17 years practice in private practice, but in the 5 or 6 years before that, I was working for a couple of practices that also had a lot of interest in these issues. When I set up the business in 2004, I really wanted to get involved in and focus and concentrate on the passive house approach to doing architecture. And the I suppose the theory of passive house as being a good building practice has been around now for maybe, I think maybe 30 or 40 years since the first passive house was built. And so it's surprising how long it's taken, given that the science has been around about climate change and how to do really low energy buildings, that we really still aren't there as a society in terms of just addressing this as an issue. And as you said, Niamh, construction accounts for somewhere in the region of 40% of all our carbon emissions and impact on the environment. And not just that, but we've got, even just besides carbon, we've got the biodiversity crisis as well, where how we're living is destroying the other, beings that we share this planet with, and it's not sustainable. So, and that's probably a broader issue than passive house, but we'll be touching on those as well. And I suppose I brought up this image of This Is Not a Drill, which is the handbook of the Extinction Rebellion movement. And I think it's a great read for anybody who's interested in sustainability issues. And it kind of brings a sense of urgency to our need to be really bold in how we address our impacts, not just in construction, but right across the board, in transport, in food production, protecting biodiversity, all these issues. And what's evident when you really get into this is that we really have to drastically change how we live, and the longer we leave it, the more abrupt that decline in how things used to be is going to be. So we're by not acting, we're exacerbating and creating a more and more of a crunch later on. okay, things are starting to change, but essentially what we need to learn to do is how to do more with less. And what that's trying to say is that obviously we understand the less part, that we're going to have less emissions and less biodiversity impact and all these kind of things, but we still have to learn how to do more. So it's about increasing the efficiency of the resources that we use. But we've got growing populations, and people have anticipations of, they're not going back to living in wigwams. So we've got to deliver comfort and exceptional buildings and exceptional architecture, but do it with less materials and less waste of energy. And that is why Passive House is the answer, and it's the only answer to how to do create buildings that are comfortable, but really deliver on a reduction in energy. And when I say it's the only answer, what I mean by that is that it's a scientific method with 30 and 40 years of testing and remeasuring and confirmation of your anticipated design energy consumption and measure of the building. A lot of the other methods that are out there, they aren't tested in the same way. They aren't as rigorous. There's more wriggle room and more ambiguity. So you can without naming other methodologies, you can tick all the boxes of how this is going to be a fantastic building, and you go back and measure it 5 years later, and you have 2 or 3 times the emissions. That can't happen with Passive House, because all the gaps are plugged, and there's external testing, or not testing, but verification. I can't certify my own building as being a Passive House building. I have to collate all the information, photograph everything on site, and hand that over to an independent third party who has the freedom to say yes or no, you've met the criteria or not. And you'll fail the first number of times you try and do a Passive House, because there's a learning curve. But you'll learn what to look out for in terms of the implementation of these buildings. And then you can start to do it reliably and deliver them reliably. So that image on the left there shows a low energy house. It's a graphic that's been knocking around for a few years, but the idea is more or less the same, that Passive House has a drastically lower level of energy consumption to even current good practice and current building regulations and current what we call NZEB, nearly zero energy buildings, which are good, but still not at the Passive House levels. And from being an architect who does buildings that are Passive House and does buildings where the brief may not be to do a Passive House, but to do as good as you can without going that extra step, and obviously complying with the building regulations, I know what the gap is in terms of when you can let yourself off the hook with other buildings that you can't get away with Passive House. So there is clearly a gap, and it is those opportunities to let yourself off the hook that create what we call the performance gap. And the performance gap is this phenomenon in understanding the energy performance of buildings, where it's the gap between what the building says on paper it's going to do in terms of energy consumption and reality. And that can also encapsulate physical effects on the ground, like have you eliminated the risk of mold and condensation and all those kind of physical with health risk implications. And you can, although the building regulations say we're supposed to eliminate these, it's still possible to tick all the boxes if you're using that as your performance, your goal, and still have failures. And there's a range of things. Overheating is another one that, in theory, we're supposed to eliminate with Part L of the domestic. It's not there in non-residential buildings yet. It will be there eventually in the building regulations. But so these are things where you can end up building a building that ticks all the boxes and still is very uncomfortable, if not impossible, to live in. So Passive House cuts through all those, and it really is, from a designer's point of view, it eliminates all these risks and helps you design buildings that really work. So yeah, about 15% of the energy of a conventional building is what we can get down to with Passive House. approach. The other thing, just to kind of put into the picture, is the Architects Declare movement. So this is a kind of a concept that's new and emerging across internationally, where various professions, in this case it's architects, but engineers are doing it, or other professions are signing up to a voluntary declaration to go to deal with the biodiversity issues and climate change issues, and to, you know, stand up and say we're going to work to best practice and change how we work, because we all accept, no, it's pointless pretending that every architecture practice is acting to best practice, because it's just not the case. There's so many things that all of us can improve in terms of how we provide professional services as architects. And you'll see if you read through this list, it's things like inspecting our post-occupancy evaluation. This is where we go, even when we're finished our services as architects, in the conventional sense, we go back for a year or 2 years or 3 years and test the buildings and put in recording of temperature and humidity and energy consumption, and just ask ourselves the question, is this building performing the way I hoped it was going to, or I set out to design it to? Because conventionally, after the client has moved into a building and the contractor has completed their snags, we'll say, for 12 months after it, you walk away from that project, you put away the file into an archive, and you hope to never hear from that client again unless something has gone wrong. That's not good enough, because you never learn from your mistakes. You have to close the loop of information coming back into the practice of architecture, so that you can ask yourself the hard question: did I get it wrong? Did I make a mistake? And it has to be done in a kind of a, you know, in a no fault, in the interest of science and learning how to do this better attitude, that, you know, and it's amazing what it does. I mean, one of the first buildings which I'm going to show you later on was a pharmacy building, and in the first year of occupation, we found that the heating bills were just higher than they should have been, and maybe by an order of 100% higher. And that's really worrying to get as somebody who's trying to do a passive house building, and you've certified it, and you've had it certified, and it's what's gone wrong here. And it was actually something as simple as the filters in the ventilation system hadn't been cleaned from when the builder handed over the building, and it was painted, and there was sanding, and there was dust. So a bit of dust had gotten into the ventilation system, was blocking the filter. So the fans were working higher to force air through these blocked filters. And as soon as the filters were cleaned, the temperatures all corrected and everything started working. If I hadn't had data loggers in there checking temperatures and giving me information back, and be asking the client the questions, so what are your heating bills, or, you know, what's going on here, that mightn't have been spotted, and that client could have become very disappointed and disillusioned. And, you know, I guess what it's showing you is that not being afraid to go in there and gather data and test the building and observe it, it can really get you out of a hole and make you not, you know, make the simple mistakes can be avoided. And that's one of the kind of obligations of signing up to Architects Declare, is a commitment to do that more, and to include it as a standard service, so that it isn't an optional extra that you offer the client. Well, listen, I charge you an extra €1,000 for me to come in and inspect this for a couple of extra, you know, to do extra follow-up. You try and include it as a standard service, and say that this, and maybe try and encourage the profession of architects generally to write that into our standard services, so that everyone can do it, and not kind of put on the blinkers and pretend that everything is fine. And there's lots of good stuff in there that are way more than passive house and low energy consumption, that deal with biodiversity and, you know, do we demolish buildings, or do we try and retrofit them? And you know, I'm not saying you can never demolish a building, but maybe have a good reason for it. So that's something that's helping to change the practice of architecture. A little bit of I suppose of the science of what is a passive house, how does it work, and what are the kind of basic principles of it. I won't get too technical on it, but technical enough that hopefully it'll get the picture across in terms of how it works. So it's a building standard for ultra low energy buildings that require little energy for space, heating or cooling. That's kind of self-explanatory. But what's really critical is that achieving defined standards of comfort. So there are criteria in the software that we use to model how the building is going to perform that guarantee the outcome of the building having a perception of comfort, that you're not going to have cold spots, that you're not going to be overheating, that you're going to have really good air quality. Because without those, everything fails, because people start to compensate by opening windows or turning the heating up, or it just doesn't make sense. So you have to have defined levels of comfort whilst reducing the energy consumption. And that connection is hard to do in terms of energy modeling. You have to go to a certain level of complexity. But the thing about the PassivHaus software and approach is that they've tried to keep it as simple as possible. Like, they're not putting in stuff there for no reason. But there's a lot more in that approach than there is in just building regulation compliance, that method of designing buildings. And what it entails is high levels of air tightness, high levels of insulation, understanding the solar radiation, what that's contributing to your heat load, heat recovery. So it's giving you constantly filtered fresh air, but doing it in a way that doesn't just pump that fresh air out of the building and lose a load of energy while doing that. And then elimination of thermal bridges. And thermal bridges is a really kind of a critical thing that is part of the building regulations, but it's just so much more robust in terms of PassivHaus. How we model all these complex junctions that are in a building, which is where you tend to lose heat. So it's not through the kind of the general plane of the wall, it's where the wall meets the window. That junction gets complex for various reasons, for weathering and structural reasons, and that's where the heat tends to escape. And you have to you absolutely have to change how we address those construction details to create this building that is not like a sieve that has all these holes that are leaking heat. And then what does the PassivHaus feel like? And I suppose this is a critical question, a critical concept, that the beauty of the PassivHaus approach is that everyone who's ever lived in a PassivHaus or worked in a PassivHaus rave about how you feel in it. And it's not a feeling of smugness because you've not injured the planet. You know, it's not an abstract or a kind of an egotistical sensation. You know, it's a real physical feeling of air quality, brightness, a lightness that you can only experience if you're in a building where you're not radiating heat, and kind of your body is kind of working hard to compensate for drafts and all these things that we're doing without even thinking. Our bodies are compensating for discomfort. And when you're in an environment that has very stable temperature and really good, clean, filtered air, we kind of don't understand why we feel so good. And this is a quote from a client of this pharmacy building that I completed. And as well as being chuffed, the clients being really happy about energy consumption and all the fantastic things that we achieved with it. For me as an architect, the most rewarding thing that I will never forget is the fact that they're saying that all of the staff who work in this pharmacy at the end of the day go home from an 8-hour day or 9-hour day on their feet feeling less tired. And that's phenomenal. I mean, so they have this kind of well-being feeling that the building is giving them, the architecture is giving them, that's supporting them as users and occupants of a building. And like, that really is, I think, a rewarding type of architecture to produce, where people, you know, they're really grateful to live and work in these buildings. And I just want to move, the screen there, sorry. So the question is, what kind of buildings have I done? What kind of experience have I suppose? I'm just going to run briefly through a few different projects to kind of give you a bit of background context on the work that I've done. So this pharmacy building is a new build commercial building. And then I'll be looking at a retrofit residential building, a home extension, a retrofit commercial building, and new build residential. And all of these things, all of these different building types, whether the new build or retrofit or residential or commercial, I want to show that the principles of PassivHaus low energy buildings are kind of consistent across them. The approaches are consistent. Obviously, the usage pattern of these buildings slightly changes the energy modeling and kind of them, but essentially Passive House is broad enough and is nuanced enough that it can address a huge range of building types. So this new build commercial building, it's a pharmacy in Clonmel. It's kind of where I went to school. I grew up in Tipperary, and this is the main street of Clonmel, the West Gate, which is kind of the walled part of the town. And this is my client's pharmacy building, which is in the family for 3 generations of pharmacists on that property on the main street in Clonmel. And so the brief was to turn that from a terribly unheatable building, uncomfortable, where the client would have coats on in the back office, and still be cold. It was so poor in terms of performance, into something different. And so we retained actually part of the structure because we were supporting the buildings on either side of it, and then completely demolished and rebuilt the building behind it. And there's a laneway running up one side of it underneath this part of the next door building, which kind of leans over that with an alley laneway access. And that gave us an opportunity to put an apartment over the pharmacy from a stairs off that lane. So this is a cross section through that stairs, if you like. So we have this 1.5 story shop floor of the pharmacy coming back to a 2-story mezzanine back of office space. And then we've got a two-story, 2-bed apartment above that. So that's kind of the completed Passive House building slotted into the existing context of protected 18th century structures here and a 1960s concrete frame building there. And there's the laneway access underneath. And there was a host of construction challenges of building in an urban centre with no rear of site access, but it was still possible to do it. And that's kind of the image then of the shop floor with the double height space behind, and that's the shop counter. 1.5 stories at the front, getting lots of light in, solar control to get to stop overheating, which would be an issue if we didn't address it. And then that's an image of the apartment at the first floor level looking out to the rear. And I won't spend too long on each of these projects, but just to give you a quick understanding of the results. So we achieved excellent comfort. Client turnover went up. A huge sense of civic pride in Clonmel for this, to have a Passive House building. Ireland's first, there's only been 3 non-residential Passive House buildings in Ireland, and here's one of them, the first Passive House pharmacy, probably, there's not many of them in the world. And it's an opportunity for learning then, like the local secondary school students come in here and do projects as part of their transition year on Passive House technology. And people are really interested in it. As I said, the well-being of the staff is greatly improved. And then about a 90% reduction in the CO2 emissions compared to the building that we've replaced. And we've also reintroduced a residential use back into the middle of the town, which is really important because we all know about the hollowing out of towns and car culture. Here's a 2-story, 2-bed apartment in the middle of town. There's no car parking spaces, and the client took a punt, in fairness, that this would be lettable. There was no guarantee that it was going to be lettable at all, and what turned out was the opposite. Multinational companies, American multinational companies based in Clonmel, took up a rental on the apartment for staff of theirs that were coming over on sabbaticals from the States to do, say, 6 months training in Tipperary and then go back to the States. And the first group that took it loved the building and living in town so much, and living in a Passive House and the air quality and all the rest, that the company immediately signed a 2-year rental contract for their staff to cycle through it, and then renewed it 2 years later for a further 2 years at a premium that you would not get for an apartment in a small Tipperary, market town. So the client is delighted, and and also now you've got a multinational that's really aware that their staff are living in a Passive House, and they're going back to the States going, what are we doing with these really dysfunctional buildings? And so it's helping to spread and disseminate that as an idea, which I think is great. And that's the Passive House certificate being handed over by me to the client, and that's the builder. And I just raised this to kind of say that the certification process is the difference, that an independent certifier, going back to Germany, to Darmstadt, where the institute is, has looked at all the information that we produced. And if you do all the hard work and demonstrate that you've actually built a passive house, then you get the privilege of putting up a plaque on your building saying this is a certified passive house. And that really is, you know, the benchmark of quality then. And that building then also won the RIAI award in 2015 for the best sustainable project. The next quick project is just to show you, again, for a bit of variety, a retrofit residential project. So this is on College Road. It is a 4-bed detached 2-story house. This is the existing building before we renovated it. And then a complete renovation, wrapping the whole building in insulation, triple glazing, dealing with all the air tightness, and then building on a passive house extension to it. And again, that's Enerfit, which is the retrofit equivalent of passive house. So the next project then is a commercial retrofit. And this is a building that I completed it's in Castlemartyr. And this is the main street in Castlemartyr, if you're aware of that, East Cork town. And you have the humpback bridge that you cross on your way to Waterford. So it's right adjacent to that. And you can see it when you're at the traffic lights at that point. And behind the main street, you have this Methodist church. And this was a Methodist mill built at more or less the same time as that. And it would have been a woolen mill. There's a stream here which would have powered it. And over the years, it had been, there's a kitchen manufacturing business. And these were their spray and workshop areas, storage areas, these sheds all around it. So the building had become lost in the middle of this cluster of light industrial buildings. And the brief from the client, who is the kitchen manufacturing company, was to get rid of all this, demolish their old leaky building, and turn this into a state-of-the-art main office building. And we had looked at, in fairness, like it's quite a difficult thing to do that with a building that's 200 and something years old. And we had looked at just ignoring that building and doing a new build passive house office building, which would have been cheaper than what we did with this building, but the client decided this building had enough quality and was exceptional enough that they would not kind of turn their back on it, and they'd take on the extra cost of renovating it. And this is what we started off with. This is the existing building. You can see there's cast iron columns, these north-facing roof lights, which would have been state-of-the-art architecture 200 years ago for light industrial, really good daylight. You know, you've got really good north light, so you're cutting out all that strong, direct southerly light that would cause glare, and you get this really even light from the north. So you know, it actually was a fantastic building in its day, and really delivered a good environment compared to what people would have been used to at the time. But with these lovely existing brick rooms off this large open plan space, and that was kind of what we were trying to hold on to. So we took off all the top of that roof structure, replaced rotten timber beams where necessary. We're able to hold on to all the original cast iron. In places, we could keep some of the original floorboards where they weren't too far gone, and then the original brick walls, the majority of them were salvageable. And the approach was, once it was cleared out, we put a roof on it and then super insulated that underneath, dealt with all the air tightness. We had to rebuild part of the wall, and then the existing walls where there were brick and stone and lime mortar construction, got a lime plaster for air tightness and a wood fiber insulation on the inside. And that's critical for allow with these old buildings that have lime in the walls, you want to leave the water vapor move through them. It's called breathability. So this, there was a cork insulation in that lime mix, which starts to improve its thermal conductivity. Then you've got really good thermal conductivity wood fiber insulation, and that has a lime plaster on it. And that creates a really good performance, but maintaining the original fabric on the outside. And again, we're able to expose the original brick on the inside where it didn't need to be perform a thermal function. But you can see the quality of the daylight here is fantastic. this is a really good place for the open plan part of the office. And then we've got cellular offices and meeting rooms around that. The original fabric tidied up, repointed, re-roofed, and that's, you know, good to go for another, hopefully, 100 years. The again, just to show you a different scale of the same approach, a home extension. This is at my own home here in Bishopstown, and this is what we had when we bought the house about seven or 8 years ago, maybe more. This is the old original kitchen from the 60s, and there was a beautiful big garden, but you know, very poor connection from inside to outside, and that's something that we're all trying to achieve these days in how we live. We want to kind of disappear that barrier between our external spaces and internal spaces. So this is the back of the house, which is kind of northwest facing. The setting sun sets up here, so cranked the plan to kind of pull this space around and capture that setting sun in the evenings, and then tilted up the roof to do the same thing. So it's like a funnel that allows that light, evening light, to get deep into the existing plan, so that this doesn't end up like a dark no man's land. And then put a continuous roof light from one side of the house to the other across that point to get that light deep into the plan. And there's that continuous roof light spanning across, and that's a quadruple pane roof light, which we want to get into as well. So really good insulation factor. Triple glaze. These are PassivHaus certified glazing, what's called curtain walling. So the glazing is continuous outside the structural part, and there's really good thermal qualities in where the glass sits. So high performance. All the thermal bridges are eliminated. Sorry, excuse me. And really thick insulation in the roof. And this is the roof light again, just showing you the kind of detailing you have to get into at PassivHaus and to reduce those losses at junctions. So you can see that there's kind of a junction here. There's actually a glass at the upper level, which is what we call a rain screen. So that's doing all our weathering. But the space between it is actually pretty much cold. And the heat, the thermal boundary is down as much as possible in line with the wall and roof insulation. So, but instead of having a triple glazed unit up here, which would have created a kind of a tenuous connection at this point, we separate the two and drop the triple glazing down into this insulation, and we get insulation here above it. And then the next image just shows you what's called a psi calculation, or it's showing you the heat flux across from going from warm to cold outside, and it shows you how the insulation affects the rate of heat flow through those junctions, where it gets more complex and there's less insulation at these kind of pinch points. But that still is really a good indication, and it's performing quite well in terms of potential heat loss through that. That's the kind of level of science you need to get to with PassivHaus buildings, and that's really the difference. Okay, so this is a recently completed PassivHaus in Bandon, and this one, when the client, we're really fortunate, and you can see down here there's a large field where the client had an option of placing the house in various locations. And when I visited the site, I kind of recognized the opportunity that there was this mill on the horizon, which is in Overton. It's called Overton, I think it was Cotton Mill, and by the Allman family. And depending on where you stood in the field, if we were 5 meters up this way, by parallax, that on the horizon would move somewhere down here in the middle of that contour. And if you were 5 meters down this way, it would kind of arrive up here. So at this exact line, if you like, you get a conjunction of the mill between the cleft of that and that hill. And that was kind of a nice starting point to set that up as an interesting kind of focal point on the horizon. And this was just a quick sketch that I did when I was there on site, just showing you this idea, showing the client that idea. So the design then, that alignment sets up this geometry where you have the dining room of the house pointing at that view on the horizon. And that geometry continues through the back of the building northwards, which gives us this the ability to orient all the bedrooms on the eastern side of that block so that they're all getting morning sunlight. And then the rest of the living functions, your kitchen, dining, and sitting space, radiate around that geometry to track the movement of the sun during the day. And that's not particularly a passive house necessity. That's just good building practice to get really good daylight quality. So as the setting sun is over in the kind of west, it's shining into your living space, etc. And then because the fall of the site is quite dramatic, the idea was that we put in a series of terraces so that the floor levels would address that change. The building would kind of sit on the landscape rather than cut into it severely. And then the other idea was that the client wanted quite a discrete house from the public domain, from the road, so which is up at this end. And the idea was that we would have a very blank facade facing the public road, but also would take the opportunity to just roll that landscape up onto the roof of the building, so that over time, when this becomes planted over the next couple of seasons, this will become very discreet. There'll be planting here, hiding that kind of car parking area. You'll have a blank facade. So the building is mute as you approach it, but then on the opposite side, it's almost fully glazed and very, very open. And this is your plan. So this represents where the landscape is ramped up onto the garage, and you've got this very solid wall facing the car park, and that's the gap between the two is the entrance. And as you enter, you've got a long corridor with the bedrooms off it, but you enter into this open plan radiating space. And that's an axonometric drawing. So that's the ramping up of the earth onto the garage. You have your living space getting the western setting sun, your dining space facing that view, your kitchen space kind of getting the afternoon daylight and sunlight, and then your bedrooms getting the morning light. That elevation is the bedroom. So the idea was that I was going to try and group all the bedrooms together and have continuous floor to ceiling glass that would bypass each individual dividing wall between the rooms. So it'll be consistent on the outside, or continuous on the outside, and wrap around the north elevation. Then we've got a blank wall where behind we've got some internal services like our utility and plant room. And then this is the north elevation. So that's where the bedroom glazing wraps around. You've got a larch cladding on the ramped, the earth wall that's behind the retaining wall. This is the kitchen, dining, living room, and the garage underneath the earth. And the idea on this facade then is that, again, floor to ceiling glass, but you can't do that in a low energy building or passive house without addressing overheating risk, or at least mitigating it. So the glazing is set back from the edge of the building. We've got these deep, kind of a meter or more projections over the head of the window, and also the side walls as well. So as the sun is rising, it can give some lateral shading across those facades. And if you don't do that, and you put a lot of glass in either a passive house building, but even a low energy building that's meeting just the current building regulations, and it's south facing, that building will overheat. And the building regulations have a tiny little paragraph that tells you you've got to address that. They don't tell you how to do it. And I think the software that you get for compliance with the building regulations has a little bit that I think is supposed to address that, but you really shouldn't be relying on it. It's not sophisticated enough, in my opinion, to address that as a risk. And it is a significant risk, because if you overheat these buildings, even with opening all your windows and doors, you're not going to be able to dump by ventilation the amount of overheating you're going to have. And you're going to have very unhappy people who can't sleep at night because the building just can't cope. So you've got to address that. And architecture has to evolve and respond to that. So that's what's happening on that facade. And this is a quick sketch kind of showing the main approach to the building. And again, we have the ramped retaining wall on one side, with the idea that we're planting, tying that, dissolving that back into the field landscape. And then we'll have this very plain larch clad wall with these sculptural downpipe details on it. And the only kind of alleviation of that will be this where those two meet and have a glass entrance. And that's kind of what we ended up building. And these are the kind of sculptural rainwater elements. This was kind of the first building where I had to, because of the complex geometry in the plan, I had to go on site when the builders were setting it out. Normally a builder, if you give the builder a rectangular plan, they will set it out on site themselves. So all you have to do is give them one dimension from a boundary or 2 dimensions and they can find it. I had to go and give them extensive cross references to triangulate how to position this building, because it was really critical that when you're the center of the dining table had to have that had to end up with the mill in the right spot. And if we started off in the wrong point, it just wouldn't happen. The other thing then is just to give you a bit of understanding of the level of detail that go into passive house construction. So this is starting from the foundations, the cold part of the building. So this is below what's ultimately going to become our insulation level. So this is a special block that is lightweight concrete, and you can load bear regular concrete blocks on this, and when you put in your floor insulation and your foundation insulation, you've carried the load, you've transferred the load, but you have broken it thermally. So it's a thermal break. And if you don't do that, it's called a thermal bridge. If you had a regular concrete block here, it doesn't matter that you've got fantastic insulation in the floor and fantastic insulation in your wall cavities. If you've got a concrete block here connected to the cold, you're just going to lose a huge amount of heat down through that concrete block and into the floor. And if you ignore it, you end up with what's called the performance gap. Why is this building not performing? It got an A1 BER rating, but why is it consuming twice as much heat? And it'll be reasons like this. It'll be these kind of details. When you add them all up, all around the building, you do enough of these, you've doubled the heat load. This is going to be carrying a steel superstructure, steel column, and it stops at this point. And this is something that I've never seen anywhere except in passive house buildings. And it's a detail that I had to come up with. I'm sure other people have come up with it too, but I had to evolve it for our own use here. And the idea is that you stop the steel at this point and you put in a thermal break that's load bearing at that point, and then you continue on your steel. And all these have to get calculated and added up into your passive house software, and then you've accounted for all the possible routes of energy loss. And then as the building begins to continue on up, there's insulation under here. This is insulation in the cavity, a special type of insulation. These are the kind of calculations you do to look at the heat loss through those junctions. So there's that lightweight thermal block carrying the regular concrete block above it. And you can use the regular block because it's on the warm side of your wall insulation. But that junction is where you have to quantify that. And these are the kind of detailed calculations that look at the heat flux, like that roof light detail, and you can calculate that from that, how much heat you're going to lose at that, and multiply it by the length of the perimeter of the building. And that gives you this value, which is your thermal bridge heat loss factor. And it also allows us to check things like risk of condensation. And that's another part of the building regulations that people should become aware of. This is the ratio that's used. It's a figure like between 0 and 1, and 0.7 is the factor that if you're below that for your surface, your temperature factor, you will get mold and condensation. And if you're above it, you won't get mold. It's the limit at which it's safe to have your temperature factor. So we check all these at the most vulnerable point of the building to make sure we're above 0.7. And here at this critical junction, we've got 0.9. So we're well above any risk of condensation and mold forming at that point. But if you were to do that on a plan detail in the corner, in all the houses that we grew up in, we have mold in those corners where there's poor air circulation, and you've got this junction that's not great, and it's got a big surface area. And so it's in these vulnerable points that if you were to calculate these, you would find that the FRSI, the temperature factor, is below 0.7, and now you have the conditions for mold. So it's that level of reliability that we're achieving here. This is the retaining wall going into it, starting to be built. These are the foundations for the rainwater downpipes. And we'll just jump through some of these details. So what's happening here is, this is the top of this stub column that I showed you, and that there is our structural insulation. So that piece of insulation can carry the load of the steel and the roof above it, but break the heat flow through the steel into the steel below. And our floor insulation then sits on this and wraps that around. So we're getting continuity right across any of these things that would be a thermal bridge. These are all lightweight blocks. So the window is going to sit at this point. That's our wall cavity. So here's our window. There's going to be there's a big gap between the external leaf and the internal leaf. So this is cold, this is warm, and this is cold. And because that wasn't as big as I wanted it to be, that gap, I put in lightweight blocks here and here as well to reinforce make it more difficult to lose heat through that point. And these are boards. Ideally, when you want your insulation to all connect up, and there'll be points where that becomes difficult. Like if your window element is your insulation of your glazing and your window frame, it's insulated, you would want to sit that window down on top of your wall insulation, but it's not load bearing. So you got to introduce a load bearing insulant, and this is a special board that has a good insulating factor but can carry loads. So that spans across the cavity and allows our window then to sit down on this. So technically it's directly above the insulation beneath it. And this is the cavity construction. So these walls are 250 millimeters of a cavity, so it's nearly a foot. And conventional buildings now built to the building regulations would be maybe 60% of that. But not only that, these are special wall ties. I guarantee you every house that's being built now to the building regulations has steel wall ties, and they're probably ignored in the U-value calculation of that wall. It's just the way it was done. So maybe they're doing it, maybe they're not. But if you were doing it and you were trying to do it right, you wouldn't use steel, because steel is a really good conductor of heat. And you add all those up over, you could have 400 of them in a construction, and that's heat loss. So what we're using here is special wall ties that are made of basalt. They give you as much structural rigidity. They're a little bit more expensive, but they don't allow heat to transfer in the same way. And there you see, this is the kind of stuff that you get excited about when you're really into environmental performance of buildings. And this is a beautiful straight cavity with no mortar on the inside and no mortar having fallen down at the bottom of the cavity. That's how buildings were built in terms of, if you look into a wall cavity where somebody is not trying to do this, I guarantee you'll see across the bottom of the cavity a whole load of mortar droppings. So cement, when they're building the blockwork, falls into the cavity, and usually it gets left there. So you've got a nice concrete connection between the bottom of your external leaf and your internal leaf. And then people wonder why they're getting damp patches at the bottom of their walls. And so that level of inspection has to go ahead, and it has to be explained to the contractor. There's no block layer in the country that automatically does this. And there's no main contractor that looks to eliminate it when they're supervising it. And if the architect isn't looking for it and giving the builder prior warning, then it will not happen. So I would explain to a contractor that we are not going to be accepting any mortar droppings in a wall like this. Sometimes I will say to them, have a think about leaving out a block every 3 meters at the bottom of the wall, so you can get in there and pull out all the mortar. And some of them will do it that way, or some of them will find another way of keeping it clean. But once you give them prior warning, then you end up with the good result. So again, this is me just looking down into the cavities and just looking at where are we? That's the cavity. This is the cold part of the internal leaf, or sorry, the warm part of the internal leaf. This is the cavity at the window. So when this is pumped with insulation, we'll have insulation in here, and then we'll have our windows, and the whole thing will connect up. So again, there's where the window will sit. You'll have a thermal break here, and then a continuous wall cavity. And then your steel here going down to the foundation is thermally broken. So all these thermal connections are separated. And it comes down to kind of, you end up, once you start, you can't stop. So we would have designed this building so that the timber roof joists would sit into the flange of the steel, and that steel would have insulation on the outside. It's not a completely cold structure. But then we realized that, hold on a minute, we can just put a double trimmer at this point and connect all our roof timbers to that and create a full void from there to there. So now if this is all filled with insulation and this is insulated, there's only one little connection of timber from a lot of that roof structure back into the steel at that point. And of course, we checked that with the engineers, the loads are fine. So why not eliminate the thermal bridge if you can? And it goes beyond that as well, that once you learn about the physics of buildings, you begin to understand how to do things like how to design a roof that doesn't have condensation risk. And when you're doing flat roofs, it's really important to get them right. It isn't a flat roof, it's a zinc roof, it has falls on it, but it's a ventilated roof structure. And this diagram is just showing you where all the vents are, continuous vents within that zinc roof buildup. And you won't be able to see them unless you know where to look for them. But essentially this little diagram is working out with the contractor how to ventilate that larch clad wall once the parapet goes on. And the idea is that our continuous larch on the outside will be here with a nice minimalist kind of capping on it. But on the inside, let's create a ventilation channel that tracks down here. And this is your the top of the insulation layer. And this is the continuous ventilation that runs underneath the roof, and the zinc will be laid on top of this. So we've got this lovely big chunk of ventilation that's keeping that roof dry. That's looking into that ventilation air. So this has nothing got to do with internal ventilation. This is just protecting the roof. It's totally separate. It is just good detailing. And this is where that ventilation gets from the gutter up into the roof at all those peripheral junctions. And then we're into kind of internal detailing. This is air tightness around the roof light. We'll move on from that. Another little image that I think is nice is just showing you, okay, this is trying to explain to the contractor, how are we going to finish this gutter, this downpipe detail in a way that is nice. This is where our large cladding is going to be placed. So I take a photo of that and sketch over it. So this is going to be our rendered facade at the rendered blockwork. We'll return the coping piece around. We'll build a zinc hopper to catch the rainwater as it comes out through the roof. And then it turns out quite neat. This is just some internal shots of how the roof structure has to be built. Air tightness is a critical thing that's really difficult to get right first time around with passive houses. And it requires forethought and explaining really explicitly to the contractor what the plan is. And it comes down to things like when the steel is going in at the very early stages of the project, a membrane has to get inserted at this point that allows a connection later on in the project, in the scheme of things. And there's another one here at this point. So as the internal blockwork walls are being built, that membrane gets put in before the wall plate, timber wall plate, gets put on top. And that sits there for 2 or 3 months until later on in the process, when your air tightness detailing, I'll just flick forward, is being installed. So here where air tightness is being installed, that membrane has been put in 3 months beforehand and allows us to get continuity from this room over the dividing wall into the next room, over its dividing wall into the next room, so that we get continuous air tightness line all the way through the roof structure. We also have to photograph and inspect all the insulation for the Passive House Institute to verify as a third party. So I've got to go around and photograph a measuring tape showing that there's 350 millimeters of mineral wool at this point, and likewise at every other location through the building, floor, everywhere. And those have to be put into a folder and uploaded with your certification data. And if they're not there, you don't get Passive House certification. So there's a whole level of quality assurance that goes into Passive House buildings that you don't have with Ireland's building regulation compliance, which is a self-certification system. Basically, I design my own building, I go and inspect it, and then I certify at the end that it was built perfectly. And nobody checks it. And unless there's a lawsuit at the end, nothing ever gets inquired into. So again, human nature is human nature. You will have you'll have a time when something doesn't happen the way it was supposed to happen. And you kind of make a professional judgment. Is it really important? Does it matter that much? Are we likely to see a problem? Are we likely to get a damp or a condensation patch here? You kind of go, well, look, let's just drive on. We're behind time on program. I'm not going to tell you to undo that thing. Things kind of, and 9 times out of 10, they mightn't become a really significant factor. But again, there's your performance gap, because you add a few of those up on, on every project, and, things don't happen as good as they could. So having a third party, having me have to submit my own certification data to a third party, I'm going to make sure that I'm breathing down the contractor's neck, because I want this to be a passive house and I need to have the proof. So, and things like the air tightness, all these really demonstrate that the building they should give assurance to a client that there's a really good chance that this is going to perform the way it was designed to perform, and they're going to get the building that they thought they were going to get. Again, just quick description of the level of detail that goes into passive house and the elimination of thermal bridges. So again, this is another roof light similar to the one that I did in my own house, where we've got the triple glazing down lining up with the roof insulation. And of course, it's much easier to buy an off-the-shelf roof light and put it up here. But it won't perform anywhere as good as this, because what we've done again is we don't really care too much about the losses up at this point, because we've dealt with the thermal losses down here and this connection. So this really is a rain screen. We've still put some insulation in here, and it's detailed well from a ventilation, kind of a air tightness point of view, and condensation risk and all these kind of things. But it's far superior than an off-the-shelf, even top-of-the-range PassivHaus certified roof light. You can buy them, and they come with a special upstand, but it'll be as good as this, but this is poor compared to having the thermal event down here. And then we get air tightness coming up, connecting to that glazing. And that's how the finished detail ends up looking. And then things like the window installation. Again, I mentioned before, this allows a good sill detail around the window. That's where the window meets the wall, low thermal conductivity blockwork, good cavity that's been pumped. And then air tightness. So the window gets taped back onto the wall, and this all gets plastered to give connection between from concrete masonry and the wall in terms of air tightness. And there's a really high performance air tightness standard that's quite hard to achieve with PassivHaus certification. It's about 1/3 the losses of what you'd be expected to reach, maybe even less, maybe it's 1/5 what you're expected to reach with building regulations. And then we do things like we have to think a lot about services, because you can build all these wonderful airtight, super insulated structures, and then you get a subcontractor doing either mechanical ventilation or electrical installation. And if they're not on board and you haven't pre-thought how those services are going to be accommodated, the first thing that'll happen is a guy will slice into your air tightness membrane, run some cables out onto the solar panels on the roof, and not tape it up again. You plaster over it, and you can't pass your air tightness test, and you don't know where the leak is, because that's what happens. So by designing out those risks, so the air tightness layer is up here, and we're putting in 100 millimeters of an insulated cavity below that can handle you give plenty of room for all your wiring, for your recessed lights, for your duct work to happen, and there's no excuse at all for that air tightness layer to be punctured. And that building now is ready for in this image is ready for plastering. The larch timber cladding is about to be installed outside. That's the larch complete. The superstructure complete. And at this point now, the building is ready to be occupied. We still have all our external planting to be done next spring and this summer, which will again really mature and settle that building into the landscape. But here you can see the solar installation. This is the grass roof coming onto the garage, the zinc roof with these significant roof lights over it. This is the terracing as the building kind of steps down with the landscape. So that's the living room facing the western setting sun. There's the orientation towards the mill, kitchen, bedrooms facing rising sun. That's the entrance. That's the main corridor with the bedrooms off it. Kitchen space, which has a roof light that's the exact same footprint as the island. This is the Jack and Jill bathroom, which is actually a fire escape. So you escape through your shower. This is the guest bathroom, which has a lovely bath underneath a continuous roof light. That's the kitchen dining space. This is the shading. This is taken in winter. So the idea with these is that the winter sun being lower gets deep into the building. But when the sun is high in summer at a high angle, these throw shading then across the glass. And that was just to remind you, that's the original sketch of the idea of framing that, the mill gable in the hillside. There's me explaining to the photographer what we're trying to achieve. And you can see there's the mill nicely framed at that point. In terms of the heating, that's the PassivHaus criteria in terms of the heating load for the building. 15 watts per meter squared, and we're at around 12. So a good factor of safety margin of error below PassivHaus standard. Yeah, 15, and we're at 9.9. So we're 2/3 of what a PassivHaus could be. And we achieved our air tightness and very low primary energy consumption. And that's how many kilowatt hours per meter squared per annum we're producing of electricity from our solar panels. And in terms of our building energy rating, the building was an A1, which is great. PassivHaus doesn't always need to be A1 because, as I said, the building energy rating, it's not really what you should be using to design low energy buildings. It's not nuanced enough. It's not explicit enough. There's so many things it doesn't take into account. But in this case, yeah, not only did we get an A1, we got a minus figure on the energy consumption because of the solar photovoltaics are producing enough energy, and minus figure on the CO2 emissions. So that's a bit nonsensical because obviously it is consuming some energy, that it does have some carbon emissions, but it's too efficient for the building energy rating system. And if any of you want to browse this building because you can't do site visits anymore, there's an online, the whole building has been mapped digitally. So you can go on with that link and you can walk through the building, and this is a live 3-dimensional walkthrough. So you can move outside the building and you can move through the whole thing. So here's our kitchen space. There's our living area facing the setting sun. For those of you who are interested in technology, you've got your plant room here. That's your heat recovery ventilation system with the ducts, with the cold, fresh air coming in, and that's been preheated with the warm exhaust air going out, and then it's distributed to the house. That's your heat pump that converts electrical energy into hot water very efficiently, and that's a water storage tank. So there's oodles of really hot water, but it's guilt-free hot water. So you can have the longest shower, rain forest type shower. And this is the idea of comfort. So doing an eco building and living in an eco building, we're not going back to living in yurts. This is high comfort, beautiful, luxury, but you're doing it without having a huge carbon impact. This is the Jack and Jill bedrooms. So here we are. There's our fire escape for the bedrooms. Nice little Jack and Jill bathroom. So again, these houses aren't huge. So this is being clever about floor area. It costs maybe 5 or 6% more to do a PassivHaus versus a conventional house. But if you just shave 5 or 6% off your floor area, you can end up with a really high performance building at no additional cost. I just briefly move to the end of the presentation.
That's
for the questions.
Perfect.
It's just to show you what's coming up. So this is a PassivHaus in Douglas that's on site. This one is on site in College Road. Again, we're really looking at overshading. So this is the south part, the south facing corner of the house. So we're incorporating this timber screen to throw shade on the elevation. This is an upside down passive house in Kildare, construction end of this year. And this is a really interesting one, the last one I want to finish on, which is one in Clonakilty. It's a really low carbon one. So we're not building with concrete blocks, it's timber frame, it's charred larch, facade. It's got this stealth bomber type form, which gives really good surface area to footprint ratio. So this is going to be about 1/3 the energy consumption of a passive house, have loads of photovoltaics on it. So it's going to be probably an energy plus house, but also the embodied energy then of the construction, because it's timber frame and timber cladding. It means this is really as good as you can go in terms of environmental building. And it's a replacement building. Their own house burnt down. So we're just replacing an existing building with all the existing site services. So that's what's coming. That's on site at the minute as well for completion later on this year. So any questions? There you go.
Thank you, Paul, for giving us this lecture. That was actually really interesting to see just how passive design isn't just subject to housing, it's also subject to commercial builds and public builds. And how obviously you have to adapt that in accordance to their function. I think it's quite informative, particularly for anybody who's interested in any sort of environmental and sustainable design, and how you also brought up about retrofitting, because that's a big, I suppose, thing that we're going to have to do in the future, is to look at our cities and see how they're going to work. Alice, do you have anything to say?
Yeah, I completely agree with everything you said. I think for me, I mean, watching that, it kind of feels like a no-brainer. What I was wondering was how do you think yourself that passive house within kind of the general public would become the norm, or like, do you think it's to do with kind of awareness or changes in regulations, or how do you think we would go about it?
So every client you speak to on the domestic side wants a passive house. It's amazing how forward it is in the public perception. Everyone seems to know about it. Whether they want to go to the expense and the complexity of delivering it, that's not for everybody yet. But probably, you know, if the profession adopted this and took it on board as being what everyone does, then the costs are going to drop down, and it's the same for builders and suppliers. You know, once the market matures and the profession matures, it gets easier and more affordable for everyone. And it really, like I think it's Belgium 15 years ago, they just said all buildings passive house, rather than trying to mollycoddle the building industry and, you know, not scare anybody and do it step by step and incremental, which is a disaster. It's so expensive to do it incremental, because everyone has to relearn every 3 years, and you change the building regulations every 3 years, and then you do it again 3 years later, and then you do it again 3 years later, and that's just a death by 1,000 cuts. You just jump there and go, look, we know it's going to hurt, but it's the way we have to get there anyway, so let's do it now. And in Brussels, they did that, and, you know, surprise, surprise, there wasn't a panic, and it actually didn't cost much more and all the rest. So, you know, so it could be for everyone if we just decided to do it. I think it's going to change a lot because of things like COVID. I guarantee you, if you were in a passive house building with filtered air, high air changes, and you had monitors in buildings looking at the parts per million of CO2. So if 700 parts per million CO2 is the threshold at which you're starting to breathe other people's toxins. If you look at passive house buildings, it doesn't kind of get above 300, 400, we'll say. Every other building does, because it's winter, you close the windows, and, you know, if you look at, everyone's gone back to school now, and I spoke to my little girl yesterday when I collected her, and she's like, what's the news from today? It was cold in class. So they had to open the windows because they don't know what the parts per million are. They haven't got a ventilation system. They have to open the windows just so that we don't all infect each other. If schools were built to passive house standard with mechanical heat recovery ventilation that was filtered, and you had a CO2 monitor in it, problem solved.
Yeah, I almost think that's a good note to end on. That it's just, I suppose, implementing the practice and putting it as part of our legislation and regulation. I'd like to once again thank you for being here.
It's a pleasure.
And it's a pity that we only had such a short amount of time to talk about it, but as you said, we have Paul as one of our lecturers here in CCAE, so thankfully we get to open up this discussion. But if you do want to contact Paul, we'll list his website in the bio, but it's pmarchitecture.com.
The PassivHaus, pmarchitecture.ie, or you just search for the PassivHaus Architecture Company. Yeah.
Perfect. But as you mentioned, we'll link all that below and all the information for Paul. And thank you all for attending. And thank you, Paul and Alice, for also partaking. So we'll see you.
Thanks, Niamh. Thanks, Alice. Thanks, everybody.